For my computer graphics final project, I've created a clone of the game Minecraft, where the world is made completely out of blocks. The core mechanic of the game is that we can place or destroy any block in the world. Here are some of the game features I've implemented. I can left click to destroy blocks, and right click to place them. The number keys allow the player to switch to different types of blocks. The L key toggles the directional light, which helps make individual blocks stand out when they're clustered together. The main challenges I had in this project were implementing block selection and rendering large worlds with good performance. The challenge with selecting blocks in 3D scenes is that there are potentially many objects at the mouse's cursor position. We want the block that is closest to the camera. My solution for this problem was color picking. First, I generate a frame buffer and attach a texture I can render to. Then, when the mouse is clicked, each block is drawn as usual, except into the frame buffer. Every block face is given a unique index, which is converted into RGB as the color for that face. When the player clicks on a block, we can convert the color back into a block index and determine the block and face selected. This method lets the player make pixel-perfect clicks, but at the cost of rendering the scene twice for selections. Another problem I had to handle was performance. This world has a width and depth of 100 blocks and a height of 256 blocks, which is a lot of blocks to render at once. I was able to reduce the render load by only rendering blocks that can be seen. This was implemented by iterating over every block and flagging the ones surrounded on all sides to not be rendered. If I disable collision with the C key and fly down, we can see that only the visible surface of the world is drawn. In a dense area like here, this can save a lot of unnecessary rendering. Iterating over every block to calculate this is expensive, but after the first time, we only need to update this when a block is placed or destroyed. And even then, only the 6 surrounding blocks need to be changed. We can see this in action by breaking a few blocks underneath. Only the blocks that can be seen from the surface are visible here. Another way to improve the performance was to use the texture atlas. Instead of changing the textures for each block, we can calculate the texture coordinates for each type of block and just keep a single texture. Every block has the same dimensions, so we can store the vertex positions and normals once and translate them with uniforms in the vertex shader. Since the texture coordinates are also stored separately, we can use the block type to change the offset where the vertex layout reads in textures. I really enjoyed working on this project, and I learned a lot while researching and implementing. Since the world is structured as only blocks, there's a lot of different ways to improve the design. Some techniques I've learned about and would like to implement in the future are greedy meshing, which is combining the faces of identical blocks together, and instance rendering, where you can tell the GPU to draw multiple instances of your mesh at once. Thanks for watching.